will be a mixture of a tutorial and of a review. And probably most of you know everything what I am going to talk about, so there will be nothing really new. But let's start in a systematic way. I think the whole story of Landau theory has started with these two fundamental papers that were published in 1937, in which Landau has pointed out that continuous phase transitions can be understood as a manifestation of a broken symmetry. And what's more, he put forth a thermodynamic theory of continuous phase transitions. And also, what's interesting for us is that probably there was a first mention of a possibility of applying the theory to liquid crystal phases. And then, of course, there were thousands of papers not directly referring to this fundamental work, but they were all using Landau theory as a synonym for these two papers. So let us see why it happened. First of all, there are three aspects which are inherent to Landau theory. The most important being the symmetry aspects, and the symmetry aspects appear to be exact in the sense that Landau theory appears as really a successful application of theory of irreducible representations. And that's actually what it does. And we also know that, as it turns out, the symmetry change described by the Landau theory is not only characteristic of continuous phase transitions, but also, as in the case of liquid crystals, it can give a symmetry change classification of first-order phase transitions. We know also, and I am not going to cover this subject, Landau theory fails in the vicinity of the transition. The failure is because of the presence of fluctuations, but in order to develop theory that correctly takes into account fluctuations, which is the so-called Landau-Ginzburg-Wilson theory, we need to take the Landau theory as a necessary intermediate step, because Landau theory allows us to construct effective Hamiltonians, and therefore also allows us to construct the theory which takes into account fluctuations of the order parameters. Last but not least, at least from my point of view, the application of Landau theory has also an important aspect, namely that it gives us possible bifurcation scenarios that are present in practically all molecular type of theories that can be envisaged. I mean, that means density functional theories. And I'm going also to show you some simple examples of this last possibility. So actually my talk will be concentrating on two issues, namely I will explain you the basic principles of course with examples from liquid crystals, and then I will tell you something about the connection.
Your mic is off. Your mic is off.
I should push a
There is a button on the box. It's in your pocket. The box is in your pocket.
I'm not.
What color?
Oh, I see. Now it should work. Oh, the battery. Okay. So, to tell you something about basic principles of the if time to do so, functional. Of the subject. I wanted to mention just the famous book by Toledano on the Landau theory of phase transition. There is a huge chapter about liquid crystals there, and of course famous papers by Joe Berman, Michel, Anisimov, etc. So what are the basic principles? Actually, to to describe the behavior of the system along the transition line. Suppose that we have one component system, we have pressure, temperature, phase diagram. In order to describe the situation, Landau has assumed that we have two objects. The first one is a non-equilibrium Landau free energy, whatever it means. And the second object is the one particle distribution function. And that's the interplay between these two quantities that gives us a powerful spectrum of predictions coming out of this theory. Well, we start with the high temperature phase number 1 of the symmetry G0, and then we discuss a symmetry reduction to any subgroup of G0 characterizing phase number 2. So G is a subgroup of G0, and its invariance group of the phase number 2. The symmetry the symmetries G and G0 are understood as statistical symmetries. That means these are symmetries of the one particle density distribution function. That means G0 is a collection of all symmetry elements that leave one particle distribution function invariant. G, on the other hand, leaves only invariant the function rho of x in the phase number 2. Of course, there is a basic thing to say that this is a non-equilibrium free energy, so the equilibrium properties are obtained by minimizing L with respect to the variation of rho. I should have mentioned just at this moment that practically all theories, microscopic theories of liquid crystals, and not only, have just this structure. Namely, they are functionals of one particle distribution function. And actually, there exists an exact theorem of statistical mechanics saying that we can construct an equilibrium, that we can construct a free energy that is a functional just of one particle distribution function and seek for the minima just by minimizing L. So actually, the bridge with the microscopic theories is at this level. Now, as I said, there are three aspects of the Landau theory. First of all, we have a phase of symmetry G0. Say we have a nematic, smectic, whatever, isotropic phase. And the first thing we have to do is to identify a possible subgroups of G0. Then, with this new Lech, we have to follow with the remaining 2 points which I indicated here. So let's start with the first. So let's start with the first point. Okay, assume that we have uniaxial nematic liquid, which is the most common phase observed experimentally. Then, of course, G0, the reference high temperature symmetry phase, is a combination of translations, continuous translations, and rotations, which are named here as the infinity H symmetry. That's a group of invariance group of the cylinder. So the first task of the Landau theory is to characterize all possible subgroups of G0 if we are interested in nematic as a background phase. And of course, these subgroups will be a combination of translations in 3D and rotations, so in combination of point groups. And of course, the translations could be composed of discrete or continuous translations. And the discrete translations could be in 1 dimension or in 2 dimensions, which classify, of course, smectics and discotic systems. And of course, I could have crystalline structures as well, in which case the translations are just discrete translations. But let's assume for a while that we are interested in nematics. Then you see the amount of symmetry elements, which I denoted as rotation, is a gigantic set. Actually, all of them could be the candidates for nematic-like structures. And of course, if I combine it with translations, then some of them will drop down. But in general, if all these structures could form, could be a candidate for a structure which is like a nematic one. In experiment, only some of these symmetries show up, say D infinity H, C2H, D6H, D2H, and D4H. But actually, as far as molecular modeling is concerned, we could create any model showing symmetry breaking from the diagram shown on the previous transparency. So actually, all of these structures could be candidates for nematic-like structures, and also for smectics or other more complex structures. So that's the first step. Now, so once we identify G0 and all possible subgroups of G0, we come to the second set of assumptions. Namely, we analyze the density distribution function. And of course, we analyze the density distribution function not far away from the transition line. And of course, the very strong assumption is that our free energy is analytical in the one particle distribution function, which of course does not need to be true. But apparently, in all theories like mean field or say Onsager type of theories, this assumption is completely legitimate and valid actually. So at least for this limited case, we can consider this to be a true assumption. Now, the density rho vax is composed of two parts. The ρ0 part, which is the symmetry, which is G0 symmetric, and it tells us everything about this phase number 1. And we have a symmetry breaking perturbation delta of rho, which of course is not G0 symmetric. So this small change delta rho corresponds to the symmetry reduction ongoing from the phase number 1 to the phase number 2. So that's the first step. Division of the density into symmetry breaking part and the reference density. Then the next step is to find a good way to parameterize this quantity. And of course, we do it by using all irreducible representations of the group G0. Think of these D matrices as irreducible representations of a rotation symmetry. So K would correspond to angular momentum, and alpha would correspond to the azimuthal quantum number. Now, having said that, we can expand delta rho in terms of these irreducible representations. And of course, prime denotes the omission of the identity representation, which is contained in ρ0 part. So the fully symmetric part is in here. Now, of course, I should also keep track of summation over equivalent irreducible representations, which means this index lambda. This is important if we model biaxial nematics. In the case of biaxial nematics, we may have many functions that have to be taken into account to correctly model the structure. So delta rho and its expansion is the first step of the Landau thinking. Now, the major step that allows to carry out the further reasoning of Landau expansion is to transfer the transformation properties of the basis functions into the coefficients of the expansion. you see, if I apply a G operation onto delta rho, then of course using standard procedure, I just multiply the basis functions with the irreducible matrices decay, not affecting the coefficients. But I can, of course, think of this formula in a completely different way. I may assume that the basic functions are not affected, while all transformation properties are moved to the transformations of the coefficients. And because these are small numbers, and because this actually defines also a representation for the semi-reducible representation for this basis, then of course we immediately come to the conclusion that we can forget about the basic functions and think of these coefficients of expansion as forming an irreducible representation for non-totally symmetric decay. And of course, you see immediately that this formula introduces the notion of Euler parameters, because these coefficients, all of them, disappear in high temperature phase, where the symmetry is G0. And therefore, we can just forget about psi's and think about the coefficient C, about the Euler parameters. And because of that, we can also bring completely different interpretation for these coefficients. We can take them by analyzing experiments, actually. So we can take these coefficients from the response functions, for instance. Example. In the case which in cases that were discussed already here, say for uniaxial pneumatics, G0, the fully symmetric part of rho of x would be 1 over 4 pi, and just the set of coefficients would be just the expansion of the density distribution in terms of spherical harmonics. In the more complex case of arbitrarily shaped molecule, but rigid one, instead of spherical harmonics, I would just have here Wigner matrices. And you see, in this case, the situation would get more complex because the index referring to the molecule could produce many equivalent representations of a given L. So we identified the order parameters. What's next? The next thing is to analyze in a systematic way the Landau expansion. So the next postulate is that the Landau is assumed to be analytical in delta rho, which could be translated into analyticity in terms of the coefficients ck alpha. Well, the Landau expansion should be, of course, invariant with respect to G0. So it should be a combination of G0 invariant polynomials composed of the coefficients ck. And of course, if we have a symmetry breaking, this part would be 0. So we wouldn't get any invariant linear in C. The first non-trivial term would be the quadratic one. And this term is universal, irrespective of the symmetry G0 considered. Namely, it just follows from the properties of irreducible representations that the quadratic part can always be written down as a sum of distinct degrees of freedom, sum of squares of distinct k's. Okay, summation is only with respect to the members of a given representation k. And interesting thing here is also that there is no mixing between different irreducible representations, and that's the property of irreducible representations. So I have a number of coefficients, ak, parametrizing irreducible representation, times something which is positive definite. in the case of biaxial lematics, there is a small complication in here. Namely, we have equivalent representations that carry different index gamma, if you remember from my previous transparency. In this case, one has to perform another extra auxiliary step, namely one has to diagonalize the quadratic part of the expansion. Now, suppose that we are in this regime in here. So we are in this green dot, not far away from the transition line. Then, of course, by assumption of the continuity, which was at the heart of Landau theory, we can try to do minimization in steps of this expansion. So we can first concentrate on the quadratic part, and then study systematically the effects of higher order terms. If we limit ourselves just to the quadratic part, then because it's a positive definite thing, it's clear that the minimization, if it's always positive, then the minimization would lead us C alpha k equals 0 always. And of course, that's what we meet in the phase number 1. But then, as we approach the transition line, at least one of these coefficients must change sign. So it must exist at least one k0 such that a k0 is 0 at the transition and negative in the phase number 2. Actually, if I have one component system, we may, of course, have a situation where at most two such irreducible representations do disappear at some isolated point. But say this degenerate case can be postponed, and actually we can limit ourselves to discuss the most common case, namely the situation where only one AK becomes 0 at certain temperature and pressure. In other words, we have a simple scheme for the coefficients AK here, namely one of them is being 0 at the transition line, while all others are positive, and it changes sign. So the simplest possible approximation of this temperature behavior is just the linear one. Okay, we have a positive coefficient times t minus t0, where t0 is just a point taken from the transition line. And you immediately recognize that this introduces the notion of the so-called primary order parameter, the order parameter which is actually responsible for symmetry change along the transition. So the primary order parameter is this, what's in here. All other degrees of freedom are secondary to the symmetry of the transition. So they could be taken perturbatively in the next stage of work. Yes?
In the realm of critical phenomena, you often have power law behavior as you approach a phase transition. So here you've got linearity in the temperature.
Yeah, well, you know, this is the Landau theory, which of course doesn't work in the tiny interval around the continuous phase transition. I've mentioned that on my first transparency, that actually in this regime, this theory does not apply, of course, but it can be generalized by taking the Landau theory as an intermediate step, you know. It can be generalized to include fluctuations, and then everything's, it's the so-called Landau-Ginzburg-Wilson theory. Okay. So we have a notion of the primary order parameter. We can also think of secondary degrees of freedom, other Ks that are in this expansion. And of course, the next step would be, after discussing the role played by the primary order parameter, the next step would be to discuss what secondary degrees of freedom bring into the theory. We now, having identified the primary order parameter, we can disregard secondary degrees of freedom and just concentrate on the primary order parameter, which I call C, and this primary order parameter usually has n components. So say Q alpha beta tensor, which has been many times mentioned in the talks yesterday and today, is just an example of the irreducible representation corresponding to n equal 5, and so on and so on. So the next step is to just forget about secondary degrees of freedom and to construct the expansion in a systematic way. And now interesting things come up. One of them is saying that having had this irreducible representation, I have only a finite number of invariants that can be constructed out of the components of Cn. This is the so-called integrity basis of the symmetry group. And so actually, I do construct the integrity basis, and then I, so to speak, classify, enumerate all possible low symmetry phases that can be described by the order parameter. And these are the so-called isotropic groups of the order parameter. Of course, having done these two things, which I show you in a while on some simple examples, I do global minimization, and this global minimization can be quite involved when the order parameter structure is complex. And of course, there are many methods, like ones using by Gufan, Michel, Yarich, Kim, and also application of Morse theory by Michel and Morse-Gimas to some limiting cases is also worth of mentioning. Okay, let me show you an example. Of course, classical lematics are a natural example to discuss here. So here we have a symmetry reduction from O3 to the infinity, through d infinity h to d2h at the end of the hierarchy. And this set of symmetry reductions can be described on different levels. We could describe separately the symmetry reduction from O3 to the infinity h, separately from d infinity h to d2h, or from O3 to d2h. Then I just need one parameter to describe that. Or I can use an irreducible representation, that means a Q alpha beta tensor, and start from the isotropic phase and describe the whole symmetry reduction which is in here. And that would be the Landau-Degen's theory. But let me first show you these intermediate cases, which are of interest because they show just generic cases. So, okay, that was, so I can use either Q alpha beta tensor or just L equal 2 irreducible representation of the rotation group. And the Q alpha beta, that's completely equivalent. And the Q alpha beta tensor has actually 3 components. That's the uniaxial component. So it's just the part which allows us to describe the symmetry reduction from O3 to the infinity h. And also it has a biaxial component which describes the symmetry reduction, say, from the uniaxial nematic to biaxial nematic. Or it can serve as the primary order parameter to describe a symmetry reduction from the isotropic to the biaxial nematic. The case of NU-NB reduction is just the simplest one, because in this case, Landau theory is just an even polynomial in B. So I have B squared and B to the power 4. Of course, AB should change sign according to Landau rules. And of course, that would lead immediately to the well-known case of continuous phase transition between uniaxial and biaxial. So the generic model for the symmetry reduction between uniaxial and biaxial nematics is just a second order transition. The same symmetry reduction from isotropic to nematic uniaxial goes a little bit differently. Namely, we need actually the uniaxial part of the Q tensor. And if we construct invariants with respect to the isotropic G0 state, then of course we get all powers of S entering the expansion. And of course, having the cubic part in here means that the phase transition is first order. It's a perfectly well-known case. Now, we can introduce coupling between the order parameters. In this case, both biaxial symmetry breaking and uniaxial symmetry breaking are treated on the same footing. And if we do that, we get just a theory which is a coupling between primary and secondary order parameters, depending upon in which phase you are in. An interesting thing is that the coupling between primary and secondary order parameters is just linear in the uniaxial degrees of freedom and quadratic in the biaxial degrees of freedom. Therefore, when we consider, we immediately see what happens then to the phase transition between uniaxial and the biaxial phase. Namely, it can change its character from being second order to first order. And this first order behavior is just induced by the uniaxial nematic part. And here is an example of the phase diagram where temperature is on this axis, and lambda, that means the coupling between S and B, is on the x-axis. And actually, this phase diagram is also characteristic of nematic Smecti-Gay phase transition, and that was microscopically modeled for nematic uniaxials and nematic biaxials by Sonnet, Virga, and Durand. So, as you see, a coupling between the order parameters can lead to the appearance of second-order phase transition lines and of singular multi-critical points on the line. So it could be a breakdown of the second-order transition into first-order transition. Well, the more celebrated model and more complex model is the one which starts from the isotropic phase. So if I take a full Q tensor, which comprises both d infinity h part and d2h part, and use it as an irreducible representation to describe nematics, then, of course, the situation becomes more complex because the order parameter has an intrinsic structure, intrinsic symmetries just from the start. But of course, that's interesting. It has the d infinity h part, as we already discussed, and of course d2h part. And here are how densities, one particle density distributions look like as we vary the parameters a and b. Just for comparison, I showed you here another interesting case which could be of relevance for nematics, let's say of nematics of different symmetry, is just L equal 4 part of 4th rank tensor, which is the next in the hierarchy of tensors that we use to describe, say, response functions of the system. You see that if we use this representation, we can also describe the infinity H symmetry. It would be a little bit, different than this one, because the molecules would like to have a maximal distribution on the cone around the director. And of course, we would get a bunch of other structures, a bunch of other possible nematic structures. And of course, it would be pretty non-trivial to get all this hierarchy of the transitions just at the level of Landau description. I will concentrate for a while on this case because we've been studying this quite intensively with Dave Allender. And in this case, the integrity basis is just composed of two invariants, namely trace q squared and trace q cubed. And these 2 degrees of freedom can be used to parameterize the expansion. And if we do so, we of course get a lot of possibilities. The possibility for, say that the diagrams predicted by such a Landau expansion is extremely rich. Actually, if we finish the expansion up to the 4th order, we get only uniaxial structures. However, when we include the invariants of the 6th order, we can get a transition from the isotropic to biaxial. It could be along one single point which is called Landau point, or it could go from isotropic to the biaxial nematic via line, which could have this shape or a little bit distorted one, like here. We, of course, have, again, a possibility of having a tricritical point as in here. Interesting thing is that we need, there is in this parameterization which I use here, there is a threshold for the parameter below which we have only uniaxial structures.
Do you mean, should the trace of Q be determinant of Q?
Well, the invariants that you can construct out of Q, let's say O3 symmetric invariants, are traces and determinants.
Yes.
But determinants are not independent of traces. So actually, the polynomials of determinants can be expressed as polynomials of traces. So this is actually a complete basis for O3 symmetry, given that we use Q alpha beta field, Q alpha beta tensor, okay? If we use L equal 4, for instance, as I showed before, then of course the integrity basis is an extremely rich structure. Okay. As you see, some other possibilities. Okay, that's more or less similar to what I showed you before. Of course, the transition to the biaxial nematic phase can go in, there does not need to be a direct transition between isotropic and uniaxial. The biaxial phase can be shifted down to the nematic phase. So there is a gigantic amount of possible topologies of the diagrams that can be constructed out of this simple expansion. And because of the use of integrity basis, it's just a nice play with two variables, so to speak. But there is one interesting thing that I would like to emphasize. If we have an order parameter with a complex intrinsic structure, and if we use the Landau expansion, there is a hierarchy of symmetry breakings. Namely, usually, this cannot be proved to be true in general, but for many cases connected with O3 symmetry breaking, usually the lowest order Landau expansion gives the largest isotropy group. So the infinity H is met when we have Landau expansion up to fourth order. In order to cover the 2H symmetry, we need to go, in this case, to the sixth order. It's even more complex if you analyze L equal 4 component of Q alpha beta gamma. Then, when the expansion is kept up to fourth order, as was shown by Jarich, we actually can get only OH, D infinity H, and D4H. If we go one step further, it hasn't been analyzed systematically, but say up to sixth order, you can get D2H and probably D3H. And I don't know whether one can get this lowest symmetry structure and how far you must go with the expansion to get it. But anyway, there is a hierarchy in symmetry breakings when we use an order parameter of complex intrinsic symmetry. And that, I think, is an interesting aspect. Okay, last thing. I promised to show you an example of applying this theory to study bifurcation scenarios in molecular theories. I will demonstrate that by just referring to the Onsager model. In the Onsager model, the free energy is just composed of an ideal part, P is one particle distribution function, and of the excluded volume average over the distribution function. If you do just Landau expansion of that guy, which is 5 minutes work with Mathematica or Maple, then you immediately end up with something which shows you clearly the hierarchy of irreducible representation that I've been speaking about. P2 means average second Legendre polynomial squared. That's the fourth order Legendre polynomial squared, etc. So we see a possible symmetry breakings here. You see? Instead of temperature, we have a density, some kind of normalized density in here as a parameter of the expansion. And you see that the lowest density where this quadratic part changes sign is just associated to L equal 2 representation. When this guy changes sign, all of them here are positive definite. So actually these are primary order. This is the primary order parameter of the transition, while these two are secondary order parameters. And of course, we can play with them and learn practically everything about the transition just by studying this simple example. Of course, it can be generalized. I have no time to talk about that. It can be generalized to more complex structures like biaxial pneumatics, but just let me finish on this.